Welcome to T2 Day 16 of Calculus. We will continue with our examination of related rates. In this question, a 15-foot ladder is leaning against a building, and I've already populated the question with the three words we need to start with: picture, know, and want. So we have a ladder that's leaning against a building. So we have another right triangle. So that's awesome. We're dealing with a right triangle, and the ladder is 15 feet long. That's staying the same. The bottom of the ladder, let's just call this distance x, and we'll call this distance y, just to make things pretty straightforward. The bottom of the ladder is moving away from the building at a constant rate of 2 feet per second. So this distance x is getting bigger. So dx dt is growing. And we know that dx dt is growing at a rate of 2 feet per second. Find the rate at which the ladder is moving down the wall, down the building, when the bottom of the ladder is 9 feet from the wall. So this is the top of the ladder, that's the bottom of the ladder. So how fast is it moving down when the ladder is 9 feet from the building? So we're looking for dy dt, that's the rate of change of the height here, dy dt, when, what is true? When the ladder is 9 feet from the building, that would be this distance, when x is equal to 9. So the next word is equation. We need to come up with an equation that links together the variables in our two differentials, x and y. So what's the relationship between x and y? Well, x squared plus y squared is equal to 15 squared. So now that we have the equation, we need to differentiate. Remember, we need to differentiate, find the derivative. And remember, these are both in terms of t, time. So when we do the derivative, we end up with 2x dx dt plus 2y times dy dt equals 0. And you can simplify this a little bit by dividing by 2 and end with x times dx dt plus y times dy dt equals 0. Now what did we want? We wanted dy dt. We want dy dt, so we need to plug in the rest. Well, we know it's when x is equal to 9, so we plug that in there. So end up with 9. And what is dx dt? Well, we know dx dt is 2, so 9 times 2 plus y times dy dt equals 0. We still just want dy dt, so we need y. We need y. When x is equal to 9, right there, when x is equal to 9. So the ladder is always 15, and this is 9, so we need to know what y is when those two things are true. So that's when 9 squared plus y squared is equal to 15 squared. So y squared is equal to 15 squared minus 9 squared. And you can do this out on your calculator if you want, but you might remember it's 9, 12, 15 is one of those nice triangles. So y is equal to 12. So that gets plugged in right there. You end up with 18, 9 times 2, plus 12 times dy dt is equal to 0. So when you solve for dy dt now, you end up with 12 times dy dt is equal to negative 18. So dy dt is equal to negative 18 over 12, which is equal to negative 3 over 2, negative 1.5. And it should be decreasing. It should be negative because y, it's going down. Remember, it's going down. And this is change in height, so it's going to be negative 3 over 2 feet per second right there. So again, start with picture, know, want, find the equation, find the derivative, and plug in. So we're continuing with the same situation, so the picture is the same, but now it wants to find the rate of change of the area of the triangle formed by the ladder, the building, and the ground. So we want dA dt, the change in the area when, again, x is 9. And we know the same things. We know dx dt is equal to 2. This is just the same as before. So now we have this triangle here. We know that's 15, and we have x and y, and we're looking for the area, the rate of change of area. So we need to relate x and the area, Well, the area of a triangle, and then this is the equation, is 1/2 base times height. Well, the base of this is x, and the height is y. So the area is equal to 1/2 x times y. We now need to find, we have a relationship now, we need to find the derivative with respect to t. So the left side becomes dA dt, and over here we need to use the product rule on x times y. So it's the derivative of the first, dx dt, times y, plus the first times the derivative of the second. You'll notice I just factored out that 1/2. Makes it a little easier. I like it that way. And again, we want dA dt. We want dA dt right there, so we need values for the rest here. Well, we know dx dt is 2. We know dx dt is 2. So now we know dA dt is equal to 1/2 2 times y, And again, this was when y was equal to 12. So that's a 12 right there. And it's when x is equal to 9. Remember, it says when x is equal to 9. And we need to know dy dt. Well, we know what dy dt is. It's negative 3 over 2 right here. We figured that out, negative 3 over 2. So we actually have everything we need in the equation. Now we solve for dA dt. And when you do that, you end up with dA dt is equal to, I think it comes out to be 5.25, and that's rate of change of area, and that's feet squared per second. So in this case, we had more things to fill in. We had dA, finding that we had dx, y, x, and dy, but we had all of that information already. So we're back to a rocket problem, and it's 3,000 feet away. Nice, okay. So we'll call that A and B for those points, A and B. And it's launched, so when it's, oh, that's not even straight up. I gotta make it straight up. It's going up, we'll call that C if we wanted to. And again, we're gonna call that H, and the velocity is 800 feet per second. So the dH dt, it's rising at a rate of 880 feet per second. How fast is the camera elevation angle? So what is the camera elevation angle? Well, the camera's pointed at the rocket right there. This is the elevation angle, theta. We want d theta dt, the rate of change of the angle of elevation at the moment when the rocket, how fast must the camera elevation angle change at the moment at that moment? That moment is when h is 4,000. So the camera operator will be changing this angle as the rocket goes up. How fast is that angle changing when h is 4,000, excuse me. So now we need an equation. We need an equation that links h and theta. That links h and theta. H and theta. So how are we going to do that? Well, we know actually that the tangent of theta, tangent is opposite. Remember, it's so toa. Toa is tangent's the opposite over hypotenuse. So opposite over here, adjacent, opposite over adjacent. So tangent of theta is actually equal to h over 3,000 right there, h over 3,000. So we have our equation right there. We definitely have it. We can rewrite it a little bit. 3,000 tangent theta is equal to h. So we have our equation, but now we need to differentiate. How do we do that? Well, the derivative of the left, and we're differentiating with respect to t. Both of these are respect to time. The 3,000 is just along for the ride. The derivative of tangent is secant squared. So it's secant squared theta, but because it's in terms of t, it's going to be d theta dt on the outside. And over here, it's going to turn into dh dt. We want d theta dt. Oh, that's a terrible color to choose right there. I don't know, I'll choose green here, see how that looks. Yeah, d theta dt. We want this one right here, so we need to fill in values for the rest. Well, we know dh dt is 880. So we have 3,000 secant squared theta times what we want equals 880. Well, that's helpful, and we need to now figure out this part, secant squared of theta, secant squared of theta, and this is when h is equal to 4,000. So let's just take a look at the triangle here. Again, not to scale, it's 3,000, 4,000, and we can fill this in because it's a 3, 4, 5 triangle. That's going to be 5,000. So that's the instant we want here. This is theta. Remember, secant theta is 1 over cosine theta, is 1 over cosine theta. So let's try to find the cosine of theta right there. Cosine of theta, so ca is adjacent over hypotenuse. This is the adjacent, this is the hypotenuse. So the cosine of theta, the adjacent side is 3,000, and the hypotenuse is 5,000. So that means the cosine is 3/5. So we know that secant of theta is equal to 1 over 3/5. So that means it's going to be 5/3. So this is 5/3. Make sure you meditate on this because that is a very key part of this problem. So what do you end up with? 3,000 times secant squared, so it's going to be 5/3 squared times d theta dt is equal to 880. And now you can use your calculator and you end up with d theta dt you isolate, you just do the division, is 0.1056. That's the rate of change of theta. So what units is that in? What units is that's going to be? Is that degree or radians per second? Which one is that? Which one is that? I'll leave that to you to figure out. Is it degrees or radians? Is it degrees or radians? The key, though, stays the same. Draw a picture, write down what you know and what you want, and take the derivative. I think the hardest part here was this part, but you might find different parts challenging.